We are going to look at some nonlinear scatter plots, which means you need to remember what all of your different graph shapes and types look like. So here's a quick little table with a refresher. You can always download the completed notes and have that handy. So it's going to be a quick recap of all things graphing real quick. So if you look at this one, it's x to the second power, which means if your function is degree 2, it's a quadratic. It's going to make that parabola U shape. So you always want to find your vertex first on those. So since it's in standard form, you can get the x-coordinate by doing negative b over 2a. So if you plug in your values for a and b and simplify, you get the x-coordinate is negative 3. Then you need to get your y value, so plug that in for x. And if you simplify, you end up with negative 3.5. So your vertex is at negative 3, negative 3.5. Which I'm plotting at the wrong spot in this video, but I'll fix it in a minute. It'll be fine. We're gonna plug in some more points, so pick some fairly close to your vertex. I'm actually gonna do 0 because it's easy to plug in and it'll fit on my graph, and then I'll do negative 1. I went ahead and plugged those in there, and I did negative 2 also, graphed it. Reflect across to get the other half of your parabola, and your function is gonna look like that. Okay, these are probably your favorite. It's x to the first power, plain old straight linear function. So you can use your y-intercept of negative 4 to plot your first point, and then slope is positive 2, so rise up 2 and go over 1, continue, and there's your line. If you have x to the third, something where it's degree 3 is a cubic, which kind of is that sort of bendy in the middle shape. Just plug in some x values, some positives and negatives so that you get the full shape. So if you plug those into your function, negative 2 to the third is negative 8, minus 1 is negative 9. Do some more here, that give you negative 2. If you plug in 0, you get negative 1. 1 gives you 0, and 2 gives you 7. Do a little labeling on your scale here because it wouldn't fit, so I'm counting by 2's on my y. Plot my points, and your cubic function is gonna look like that. Basically, it's your parent function translated down one. You may need to solve for y and put these into the form that you're used to make your life easier. So I'm going to subtract x from both sides, which makes it easier to tell that that's a linear function with a y-intercept of 2 and a slope of negative 1. So I can just draw that in there. This one again, I'm going to rearrange it, so I'm going to subtract that entire quantity in parentheses from both sides, which will make it by equals negative x plus 1 to the second minus 2. It's squared. If I think about multiplying that out, it'll be a quadratic, degree 2. This one's nicer because it's in vertex form, so your vertex is translated left 1 and down 2. I'm leaving my letters out today. So I can just put my vertex at negative 1, negative 2, and then get some more points. How about we do 0 and 1? So if you plug those in and simplify, 0 is going to give you negative 3. 1's going to give you, if you add that, that's 2. Squared is 4 times the negative would be negative 4 minus 2, negative 6. Plot them on your graph. My negative 6 is going to be off a little bit here, but I'll just drop it down below. And then reflect the other half. I like vertex form better for quadratics. Less work. These are one of your most recent types. You have an exponential function because you have a base that is a number and your variable's up in the exponent. So when you graph these, you can just plug in some points. I would do your parent function with your vertical stretch first, and then do your translation later. So I'm going to do negative 1, 0, and 1. If I plug those in, 4 times 1 half to the negative 1 is going to be 4 times 2, which is 8. Anything to the 0 power is 1, so 4 times 1 is 4. And then 4 times 1 half will get you 2. I still need to translate to the right 1 and down 3. So let's change our coordinates of our points. If we're going right 1, then I'm going to add 1. If If I'm going down 3, I'm going to subtract 3. So my final points for my translated function are going to be these ones in my table. I'm going to plot them. So if you toss them up there, it's going to look like this. And remember that whenever you have an exponential function, you normally have an asymptote along the x-axis. Ours was translated down 3 though, so now I have an asymptote along the line y equals -3. Now that you're kind of refreshed on your graph shapes, let's take a look at some scatter plots. So if you look at this first one, it definitely looks like it is a quadratic model. The next one, it's kind of sort of half of a quadratic, or if you think about it, sort of leveling off on the left side, it looks like an exponential model would be the best to fit that data if I was trying to make my function to match it. B is looking like the ones you did yesterday, where it's just a linear function that you could write your equation for. D could almost be linear, but it would actually be better if we used a cubic because it's got that kind of little bend in the middle. So those would be the best models for your scatter plots there. Here, to determine which model would best match your data, it would be a good idea to go ahead and plot these. I just did it for you. I didn't make you watch me do it. So if you look at this first one, it's kind of flattening out as I go towards the right. So it looks like maybe an exponential function. Also, if you do it without graphing or think about your rate of change, like your y values are decreasing by 25 and then 15 and then 7, 8, and then 5. So your rate's kind of like flattening off, which makes it seem exponential as well. If you look at this one, it looks pretty much like a straight line. If you look at your change in each y value as your x's get 1 bigger, we're changing by almost the same amount each time. I mean, 8, 11, 16, 12, 9. They're all approximately the same rate of change, which would indicate a linear function. Let's do a little bit of matching. So I kind of do process of elimination. It's not quadratic on A, so I'm going to eliminate option 4. And then I'm going to look at my slope, because although y-intercepts are fairly similar, you have to be kind of careful on your scale here. So if you think about, I'm just going to pick a couple points and go between them. Let's say I go from that point to over here. It's approximately up 10, I know it's not exact, and over 4. So if you think about your slope, we've got 10 over 4 is 2.5. The closest option we have is the slope of 3, and the y-intercept looks approximately right at 25. So if you look at the next one, kind of drawing in a line to match your data, it looks like it's quadratic. They're all quadratic, so that doesn't help us a ton, but it's also facing downward, so it's reflected across the x-axis, and it needs a negative coefficient out in front. So that gets us down to 2. If you look at your vertex, our vertex is translated to the right 3 and up 3, so it has to be that one. If you look at this last one, it looks exponential because it's kind of flattening off towards an asymptote, which all of these are. It is exponential decay because it's going downwards, so we can eliminate 2 and 3 because their bases were greater than 1. So the other two, let's just plug in an x value and see if we get close to a point on our scatter plot. So if I plug in x equals 1 in my first one, I'm going to get 7 over 3, which is 2 and 1/3 plus 1 would give me 3 and 1/3, which is somewhat close to the rest of our points. If we try the bottom one, our other option, we're going to end up with 1 and 1/4, which is not as close to matching our scatter plot as our first one. So our best option was option number 1.